Small delay there. Christian, you had your hand up. Did you have one that you want to talk about?
So for 42, how do you find the max on the calculator?
42? Yeah, let's look. Sure. Yeah, let's grab that real quick. All right. So we were specifically interested in finding that maximum height. So stop talking for me, guys. The equation that we wrote in terms of y was what is this, right? So I know that the maximum for this function is going to occur. This is like a upside down parabola, right? So the max is going to be here at the vertex. So I remember for any quadratic, the vertex is negative b over 2a. Oops. So I'll do that. That come out to be some decimal. Oops, wrong button. So 80 divided by 32. I guess I probably could have tried to do that in my head, 2.5. And then if I want then the height, I'm just plugging 2.5 in for t to actually get that height. You could also use your calculator to do that, right? If you had graphed this function, negative 16x squared plus 80x plus 5, and again, I don't know, 0 to 10, probably fine for times. And then heights 0 to, I don't know, let's say 150 or something. I don't know how tall this thing's going to get. You could do second and then the trace command and pick maximum. So left bound, I need to move my cursor somewhere left of where that maximum is. Anywhere left of it would be fine. That looks good. And then press enter. Now it asks for right bound. So just move my cursor somewhere right of where that maximum is. Press enter. And then a guess. Doesn't matter where the guess is as long as it's in between. So just press enter where I'm at. There's the 2.5. And then if I plug that in, I'd get 105. So you can do it with your calculator also. It would not be inappropriate.
Is there any way to do it in the parameters though? Because I did it in the parameters.
Oh, I wouldn't have thought to try. Yeah, I don't know. Maybe not. Maybe it won't do max and min because it's in the parametric mode. Is it not an option when you look at it? Yeah, so that's the hitch. Hannah? Oh, for how high is the, I'm sorry, in part, which one? Yeah, that's what we did here. So the maximum height is going to occur at the vertex. So the vertex will give you the time comma height. So the x-coordinate of the vertex is the time that it takes to get to the maximum height, and the y-coordinate is that actual maximum height. Does that feel okay? Tessa, you had a hand. Was it the same thing, or? Yeah? Okay. Other questions? Happy to do more. If you guys got more. Tessa? 44? Sure. And again, if I'm not being thorough enough or whatever, you know, you can stop me and ask for some clarification or ask like, hey, what if I try doing this in parametric mode? Can my calculator handle that kind of thing? Those are all good and fair questions to ask, and we'll kind of figure that out together. But, oh boy. Okay. Okay. So Matt hits a baseball when it's 3 feet above the ground with an initial velocity of 115 feet per second. Ball leaves the bat at a 41-degree angle with the horizontal and heads towards a 20-foot fence that is 385 feet from home plate. So part A, write the parametric equation. Okay. So my function for x is the initial velocity times t plus, what was it again? I should have this memorized by now. I've done it enough times, but it's one of those things like you don't want to screw this part up, because if you screw this part up, you're in a lot of trouble. No, that's it. Okay. And then plus nothing. And then I have a negative 100 and, I'm sorry. And then the y is negative 16t squared plus the initial velocity times t plus that initial height. Oh my gosh. Oh my gosh. No. It's 115 cosine 41. That's what I was forgetting. And the 115 sine 41. That's what I was forgetting. Okay. Woo! Tess, are you okay with what I did there? Yeah? Okay. It's just plugging stuff into the formula we'd given, right? Okay, for part B, it says if no fence or other obstacles were present, find the distance the ball would travel when it first hits the ground. So we're looking for an x. To find that x, what we're going to do is use y, solve the y equation for t, plug that t into the x equation to get the distance. Tess, are you good with that plan? So what value for y are we interested in? When it first hits the ground is when y is 0. So I'm going to take my y equation and set it equal to 0. And I'm going to solve this for t. How do I solve an equation like that? Quadratic formula. So I'm just going to type that into my calculator. So I like to use the fraction command to do this. So alpha y equals and then option 1. So I have negative b. So 115 sine 41 is all my b. Then I have plus or minus. I'll do the plus one first. And then b squared. So I have to make sure that I put a parenthesis around my entire b before I square it, or else it's just going to square the sine 41 part and not the 115 part, and that'll be a problem. Minus 4 times a times c all over 2 times a. I get a negative value. Well, I know that's not right. So what should I do? Well, I'm just know I'm interested in, I'm supposed to be looking at this value, right? That doesn't seem, what did I do wrong here? That doesn't seem right. Did you catch a mistake? Oh, yes. Awesome. Very good. I was in radians. Perfect sense. I was like, those answers don't make sense, and I don't understand how I made a mistake. There's my first answer. Again, negative. That's a nonsense answer. I don't care about that. There's my second answer. That seems much more probable. So 4.75-ish seconds. So then I'll do x of 4.75. So 115 cosine 41 times that answer. So about 412.7. Does that feel okay there, Tessa? And then for part C, it asks, will the ball clear the fence? If so, by how many feet? If not, will it be catchable, i.e. less than 10 feet from the ground? So here, what we're interested in, will the ball clear the fence? We're interested in it, the value for y when x is 385, because that's how far away the fence is. Does that feel okay there? So I'm going to be solving the x equation for t, and I'm going to plug that t equation into y to figure out the height of the ball when it reaches the fence. So 385 is equal to 115 cosine 41t. Divide both sides by 115 cosine 41. So that'll be my t. And again, I'm going to use that fraction command here, just so I don't have to muck around with a bunch of parentheses to get that to work. So I get 4.44-ish, which makes sense because it shouldn't take as long to get to the fence as it did to hit the ground, but it probably is going to be pretty close, right? So I like that answer. That feels good to me. So then I'm just going to plug that equation in for y and see what I get. So negative 16 times that answer squared plus 115 sine 41 times that answer plus 3. So I get 22.8 feet. And since that's greater than or equal to 10, it's a home run by 12.8 feet. Oh, it's 20 feet, not 10 feet, right? That was 20 feet fence. So it's not, it's only 2.8 feet that it cleared the fence, but it's still a home run. My apologies. It was to see if it was catchable was 10 feet, because that's probably how high somebody can jump with and catch a ball with their arm up. That's like being able to touch the basketball rim. If you're a good outfielder, you can probably do that. Maybe. If you got enough of a running start anyways. Or you step on the fence and give yourself a little boost. Hannah? Sure. Tessa, does that feel okay? So it's all about just figuring out like which part of the parametric equation to use to solve for t, and then plugging that result into the other one. All right. Oh, this is convenient because it's a continuation of the previous problem, right? Because we just did 44, correct? Okay, good. Okay. So in 46, it says, in question 44, suppose that at the moment that Matt hits the ball, there's a gust of wind that acts in the same horizontal direction of the ball at a speed of 6 feet per second. Okay. And then we're going to do the same thing, right? is a wind blowing horizontally going to affect the vertical component? No, right? So that vertical equation is going to be exactly the same it was before. Is it going to affect the horizontal component though? Yes, right? The initial speed of the ball was 115, but now we have a 6 whatever feet per second tailwind. So now the initial speed is really 121. And then we proceed exactly as we would from there. Are you good at past this?
Yeah.
Okay. So that's all that changed, right? Is that we just had to add those into the appropriate component to the initial speed. What do you have to be a little bit careful about? So you don't add it to both of them, right? It is only going in the horizontal. So we're only adding it to the x component. Oh. Other questions? Happy to do more if you guys have more. These are good questions. I can tell you guys spent a bit of time on the homework and really made some progress to get deep into this stuff, which is great. I don't want to cut anybody off if you still have questions, though, on things. Elena?
Did you do 40?
Sure. It's 42, right? Okay. All right, so this one here, we're going to talk through a little bit, right? So before we get in here, so observe that, say, for like 37, we probably wrote this, right? Okay, so if let's just ignore the center being different for this then. We know we're going to have this part, right? That's supposed to be a 1, 1 there. Does that feel okay so far, Elena?
Yeah.
Okay. So that is going to be a circle with radius square root 11 that's centered at the origin, right? If I want to move its center, what kind of geometric transformation am I doing? Like a dilation, a translation, a reflection? What am I doing if I'm just picking the thing up and moving it to a new location? That's a translation. Good job. Okay. And how do we transform the points to do a translation? If I want to move like to the point 0, 0 to the point AB, how do we take all the points in our function and change it? What do we have to add to the x coordinate?
I like the same one.
A, right? And to add to the y coordinate, we need to add b, right? So here, to the x component, I'm going to add 4. And to the y component, I'll subtract 3. And that's it. So I just build out my circle centered at the origin, and then I just translate it. The x component just represents the horizontal direction, so if I need to change it from 0 in the x to 3, just add 3. The y component is representing the y points. If I need to change that from 0 to -3, I just subtract 3. Does that feel easier than maybe you hoped, even? It's like, oh, great. So the radius we multiply to the cosine and sine, and the center we just add to it. Like, easy. Anybody else? Okie dokie. We're going to do 10-3 here, because this is, oh, maybe at least sum of 10-3. By the time it gets to like 8:40, if I haven't stopped, somebody stop me, okay? Does that sound like a deal? Make sure we have like 25 minutes at least. So if I haven't stopped by the time we get to 8:40, please stop me. Shh. All right. So this chapter is divided up into two really parts. The first part was talking about parametric functions. The second half is going to be talking about polar functions. Before we can talk about polar functions, though, we have to talk about the coordinate system. Now, parametric was easy, relatively, because we're still just plotting x's and y's. In a polar coordinate system, we're not plotting x's and y's anymore. The way we plot points is fundamentally different, and the axes are fundamentally different. So this requires a little bit more introduction. Rather than diving directly into polar functions, we have to talk about like how we even plot a polar thing. So let's start with our definition here. So in the polar coordinate system, what we're plotting are r comma thetas, where r represents the distance from that point to the origin, and theta is the measure of the angle that gives the terminal side for the point's direction. What does this sound like to you? It sounds like something we've already done. Vectors, right? What is r really? In vector talk, we'd call r the magnitude, and the angle theta we'd call the direction. So this polar coordinate system is going to be very closely linked to vectors. So all the vector techniques we used, many of them are going to come back into play here, which is great. So let's look at the polar axis. What does that look like when we draw the polar axis? So this is what the polar axis looks like when we draw this. So these circles are circles of different radii. So this is a radius 1 circle. This is a radius 2 circle. It's a radius 3 circle, etc. And each of these angles is like 30 degrees. So it's 30, 60, 90, 120, 150, 180, etc. Everybody's okay with that? So let's use this here and practice graphing some of these. So we'll color code this. So I'll do all right. So the first thing I like to do is look at the angle. So I'm going to identify a 120 degree angle. So again, 0, 30, 60, 90, 120 is this line. And then I'm just going to count out to the third circle. So that's 1, 2, 3. So that's that. Okay. If I look at the next one, again, I like to start with the angle. Pi over 3. What is pi over 3 in degrees? That's 60 degrees. You could always multiply by 180 over pi to convert it into angles or into a degree, right, if you need to. 30 degrees is also pi over 6, so you could count up by sixths. You know, like 1/6, 2/6 is a third. You know, 3/6 is a half, 4/6, you know, etc. You can count that way also. All right, so 60 degrees, this is 30, so this one is 60. And then what do we do with a negative there, right? What do we do with a negative there? Well, instead of counting on the 30 degree or the 60 degree line, we're going to reflect it the other direction and then count 2. 1, 2. Is everybody okay there? All right. So let's do part C now. It says negative 100. So remember, negative angles, we go clockwise. So negative 30, negative 60, negative 90. Negative 100 is probably somewhere over here-ish. Everybody's okay with that? But I noticed that my R value is also negative. So I have to like reflect that line here. Right? So if I kept going and extended it, I would be over there. So that would be like where I'm plotting. So I count 1 up on the circle, and there's my point. Is everybody okay there? Okay. Important observation. What if we had also asked to plot the point, say negative 1 and then 260? What's that going to give me? The same thing as the orange one, right? Because 260 and negative 100 are coterminal, right? So it's the same starting location. You do the same flip. What if I had asked you to plot, say, positive 1 and then 80 degrees? What's that going to give me? Same thing, right? If I look at the picture, that seems like that's 80 degrees and we're 1 up on the circle count. So what can we say about these polar coordinates that's different than our rectangular coordinates we've been working with all this time? They're not unique, right? The polar coordinates, you can get lots of different ways of writing the same point, which is kind of unfortunate, right? But it's okay. What that's going to allow us, though, is allows us to like double back across and create some really intricate looking functions that fail the heck out of the vertical line test, but are still would be considered functions in terms of this r's and thetas. So let's kind of sum up what we just observed here with a definition about points or coinciding points. So we say given a point r comma theta in the polar coordinate system, and just FYI, I'll use PCS as an abbreviation for polar coordinate system, because boy, that's a lot of letters to write. Any other point that coincides as P must be of the form r comma something coterminal to theta, which is what we observed here with this example, right? Or it could be negative r, flip the angle across the axis, which is what we did, right? If I added 180 to this, I'd be the 80, and then anything coterminal to that. Is everybody okay with this? So this is just a fancy way of rewriting exactly this observation that I made above, that there's kind of two ways you can find a coinciding point. By taking something coterminal, or you can flip it with a different angle that's not coterminal, right? So let's do an example of this, or using this. So it says find all the polar coordinate points that coincide with the following. So let's do part A first. So you have the situation where the R is the same. And then we're just looking at the stuff that's coterminal. Or you can have the stuff that's different. And then if I do 5 pi over 6 plus 180, that gives me 17 pi over 6. Or I'm sorry, 11 pi over 6. Everybody's okay with that? And then everything coterminal to that. Rita?
We want to add the pi to the 5. Oh.
Just using the formula that was given above. That's what that adding the pi is doing, is it just continuing the line straight through, right? Like when we did this up here, when we graphed the initial, like, come on. My negative 80 was like, or negative 100 was over here. If I add 180 to that, it gets me this stuff up here, right? That's all that adding the 180 is doing, is just like replacing the flipping the negative. Yeah. And then part B, so same idea. We'll do one where the R stays the same, and we just take everything that's coterminal. Oops. But since we're in degrees, we'll use n's, or 360s, excuse me. And then we'll have the stuff that's negative. And then 180, or negative 234 plus 180 is negative 54. and everything coterminal to that. Does that feel okay with everybody? Pretty easy, it's just a formula, right? That's what it boils down to. Worth pointing out to you, see in the formula how we've added pi or we've added 180. There's nothing special about the adding or adding part. You could have also subtracted pi or subtracted 180. That would be fine too. I don't know why you'd want to add another, like include more negative signs rattling around in there if you didn't have to. I wouldn't, but it wouldn't be wrong if you did that. Okay. So what we want to do next is we want to figure out a way to convert from polar to rectangular coordinates and vice versa. So going back, I guess we could say going back and forth here because I have both. So to go from polar to rectangular, well, I translate my x by doing r cosine theta, and my y is r sine theta. And to go from my rectangular points back to polar, x squared plus y squared gives me r squared, and tan theta will give me y over x. What is this? Does this look familiar? Yeah, right? This looks like exactly kind of the triggy stuff that we've done before, right? So again, just to kind of get a picture of what's going on. So if I plot my point r theta, there's my theta, there's my r. So if I want to convert that into an x, well, that side is just going to be, r times cosine theta. The y side is just going to be r times sine theta. Or if you have the x and y and we want to figure out the r and theta, use the Pythagorean theorem to find the r and use tan inverse to find the theta, right? These four formulas here are will be super, super commonly used. It would be something to just make sure you've highlighted and pointed out to yourself in your notes because you'll come back and use these frequently. And not just in this section, but in the next sections as well, when we start writing polar functions and rectangular functions and converting them. That'll be helpful as well. All right, so given the polar coordinate -3, 148, we want to convert that into rectangular. So to get my x coordinate, I'm going to do r times cosine theta. And the y I'm going to do r times sine theta. gonna make sure I change my mode to degrees. Okay, did that. So I have 2.54 negative 159. So there's my point. No big deal there, right? Pretty easy, just plugging it basically into the formulas. Okay, this way is typically trickier. So first thing let's do, let's find r squared. So that's 9 plus 4, that's 13. So r is going to be plus or minus the square root of 13. Now, we have a choice here. Do you want to work with positive r's or negative r's? I would always use the positive ones. I think it's just going to make our life a little bit easier. So we're just going to choose to use the positive one. Now, what I'm going to do is I'm going to draw myself a little bit of a picture here to remind myself what's going on. So like negative 3, 2 is over here, right? We're looking for that angle. So this looks like a first semester trig problem, doesn't it? So theta is going to equal 180 minus this phi is what I usually use, right? Where phi is tan inverse of the absolute value of y over x. When I do that, I get about 146.3. And I'll do that in degrees because it didn't ask me, or didn't tell me specifically to use radians or something. So I'll just do it in degrees. How's that feel? I mean, should be fairly easy, right? Guess what, guys? That was it, dudes. So 49 to 62 is the homework set for that section, and I have like just exquisite timing because we're right at like 8:40, which is when I wanted to be done by. Yes. Let's go.